Hey, finally, the last part of chapter 7. This is the easiest part, and also I try to make it a little bit funny part as well. What we are going to do in this section is we are going to compare pros and cons of all the bonding theories, and we will end our discussion with topic called delocalized bonding. It's very simple, kind of you already know, but just going to give you a heads up. So here, let's discuss what kind of theories that we discussed and what are the pros and cons of those theories in this chapter, right? Starting with Lewis theory. And each one of these theories comes with a MIMS. So here, Lewis theory is kind of like, if you know Lewis theory, you are smart. Your brain is, lighting it up. So Lewis theory, what is the strength? If you know Lewis theory is you could qualitatively predict the bond strength and the bond length because you can draw the structure and then you can use it to predict the bond strength and bond length. Like, remember n and single bond versus n and double bond versus n and triple bond. If you draw the Lewis structures, you could, comment on those things. And what is the weakness of Lewis theory is it is a two-dimensional model because you draw structure in two-dimensional model. Real molecules are actually three-dimensional, right? You just write all plane for Lewis structures and fails to explain why bonds forms. Like Lewis structure, although it is true that everything that you drew is a correct Lewis structure, but it doesn't talk about why bonds forms. It just talks about how to make bonds between atoms, right? So it's very useful, highly useful Lewis theory, but it doesn't quite say like why those bonds are formed. That's why we have more theories. So that's when comes the next high level smart stuff, valence electron repulsion theory. If you also know valence electrons repulsion theory, you are shining like here. You're like, high level smart now. What is the strength of valence electron repulsion theory? It predicts the shape of many molecules and polyatomic ions. Again, it does have downfall, which is it doesn't quite explain why bonds forms again, just like Lewis theory, because valence electrons theory is kind of uses the Lewis theory and uses the Lewis structure, then talks about how to distribute the electron domains around the central atom. But nevertheless, mastering both Lewis theory and VSEPR theory is like quite a job. And if you do all of these two theories already nailed them, congratulations to you because it's lots of hard work. Now let's see what lies ahead. What lies ahead is valence bond theory. Valence bond theory, if you know it, it's like it is smart thing to know because it does talks about how covalent bonds forms, which is one of the fundamental things, right? You know that there are atoms, but you need to have an explanation why atoms are making bonds. It is to lower their potential energy, right? That's what we discussed. So they lower the potential energy, they achieve the stability, that's why they form. And if you understand it, that's like, high level stuff as well. However, it fails to explain bonding in many molecules. It doesn't quite come across what type of bonding they were forming and how they were actually forming. Like, the example is all the bonds in CH4 are equal length, but valence bond theory doesn't have explanation why all of these bonds are equal length. According to valence bond theory, three bonds should be equal length and one bond should be different length because it uses 2s orbital and a 3 2p orbitals. That's where the shortcomings of valence bond theory lies. However, wait for the next one. Hybridization of atomic orbitals, my favorite one, my favorite pick because it is the basis for organic chemistry and I'm at my heart organic chemist. So the strength of hybridization of atomic orbitals is, first of all, if you master this, it's like out of the universe. Well, I don't want to use the out of the universe, but it's really hi-fi stuff, hi-fi, powerful, uh, um, sprinting energy kind of brain, high level energy kind of brain. You are really, really smart if you nail the hybridization of atomic orbitals. Why? Because you have the strengths of able to use this theory to explain the hybrid orbitals and explain the bonding and the geometry in molecules, explain the bond angles, and explain why all bonds, or most of the bonds are having same bond lengths, and explain why molecules having the geometry that it does have, and explain why molecule have these bond angles it has. However, it does have, some weakness, right? That's why we have the last theory, right? It does still fails to predict some important properties such as magnetism. Not whole lot, uh, bigger mistake, but it's a small mistake. But if you know hybridization of atomic orbitals, you would like, high level smart guy like this. Then comes the last one, molecular orbital theory. And if you master this topic, this like out of the universe. This is like, really, really, really cool stuff. With molecular orbital theory, the strengths are it accurately predicts the magnetic and other properties of molecules and accurately predicts the existence of molecules. The only weakness for this molecular orbital theory is it's really complex. Again, in this chapter, we didn't discuss those complex part of molecular theories. I don't know if you guys agree with me, but I have seen the complex stuff of molecular orbital theory. I have seen people getting burned out, but I just loved that course when I have taken it in my master's under part of my organic chemistry curriculum, where we spend one whole term, one whole full semester on just molecular orbital theory, just trying to figure out how this bonding is actually occurring at deep level. That's why I saved it for last, and this is like mastering the bonding. If you master the molecular orbital theory, it is like mastering the bonding. You're like, out of the universe kind of smart guy if you do that. Yeah, I try to, give some fun way of explaining difference between these theories. I hope you guys enjoyed it. And range yourself where you located. Each one of them is smart thing, all of them are really complex and all of them are challenging topics. And if you know all of them, you're, hats off to you, because challenging topics. I'm the first one to admit. That's why I put my all the energy to make sure, I can reach to all of you guys through these topics. Let's see. Now, just one, two topics, and not too complicated, and just kind of discussion, like I said. Conductivity can be explained using the help of molecular orbital theory. We can shortly call it as band theory. How you would do comment on conductivity is conductivity happens when electrons from highest occupied molecular orbital. Let me repeat that. So conductivity happens when electrons from highest occupied molecular orbitals jump to or travel to or shifted to lowest unoccupied molecular orbital. So what decides which atom or molecule is conductive enough or not conductive enough, or a semiconductor or an insulator, is the difference or the distance between highest occupied molecular orbital and highest unoccupied molecular orbital. So in your highest occupied molecular orbitals, that you can also call it as valence bond, you have electrons, right? And for a conductor, you need to have the highest unoccupied molecular orbital, which you can also call it as conduction band, really close to it, really close to it. So electrons from highest occupied molecular orbitals will jump to highest unoccupied molecular orbital, and electron transfer occurs. When electron transfer occurs, you have conduction, right? So metals have these conduction band close to the valence band. In semiconductors, which are molecules that show some conductivity but not as great as conductors, there is a really small energy gap, so it is still possible to conduct electricity by pushing these electrons to a high side, but it doesn't happen all the time, so it happens at less speed. However, when it comes to insulators, the distance between valence band and a conduction band is really large, so that these electrons cannot jump to the conduction band. That is how we can trust the insulators. That is how we can trust the insulator gloves or insulator shoes, or these materials or insulator suit, all of these. It is because in the materials that are called insulators, the conduction band is far from the valence band, so electrons cannot jump to the top easily. So we are safe. We don't get electrocuted easily if you wear insulator containing material. However, don't try to touch the electricity with a conductor material in your hand. That's like at all. Please don't do that. It's not even a joke to discuss also. That's how conductivity works. So just one or two topics here, again, just for discussion. Uh, so we discussed about molecule having double bonds and single bonds. However, in the case of benzene, electrons are actually revolving around. It is called delocalization of electrons, or in other words, resonance, that we discussed in chapter 6. What is the delocalization is electrons from one bond shifted to another bond continuously. So as a result, this structure is equal to this structure. I don't know if at this stage, if you don't get it, that is fine. It's not really necessary. I'm just discussing it. And so yeah, that's how it looks like. That's why we write benzene like this. Again, if you don't get it, that's fine. So it is asking to explain these carbonate and resonance structures, which one of these correct? Basically, all three of them are correct, because in resonance structures, basic framework is there. You only shift the number of electrons from one position to another position. If only electrons position changed and all the atom-atom connectivity is same, then you just call them as resonance structures, and they happen because of delocalization of electrons. Then you don't really call them different molecules. You just call them as delocalized molecules or same molecule. Again, if you don't get this previous one and this one, that's totally fine. It's kind of like extra information. I'm just going over because it is here. It is included in the chapter, but it's not totally, what losing your mind if you don't get it. Just move on from it. Okay. So as a summary, this is everything that we discussed in chapter 7. We started from discussing about VSEPR model, then we went on to discussing what our electron domain geometries are. Then we spent quite a bit of time on learning about molecular geometries and bond angles. And we talked about molecular polarity with the help of axial and equatorial bond angles, like if they get canceled each other or not. And then we applied molecular polarity theories on structural isomers. Then we went on to discuss intermolecular forces or van der Waals forces. Then we discussed dipole-dipole, London dispersion, and ion dipole, and hydrogen bonding. It's not listed here. And then we discussed about, valence bond theory, hybridizations, and we discussed what is sigma and pi bonds are. And we did discuss molecular orbital theory just recently, and we did discuss bonding molecular orbitals and conduction, and we discussed antibonding molecular orbitals, bond order, molecular orbital diagrams, and just now in benzene example or resonance structures, we discussed delocalized bonding. These are all hardcore, challenging topics, and if you get all of them, tip of the hat to you. And if you don't get them, I'm here for you to help, or you can rewatch these videos again. Or we are going to discuss and practice problems on these. We have time. It is normal to feel they were challenging. They were challenging topics, and it is normal to feel like lost. Normal to get frustrated. But you will go through those phases with the help of these videos and with the help of me, and I will make sure you are comfortable in learning these topics. So that's all. Again, just like previous chapter 6, I thoroughly enjoyed talking these topics and explaining these topics to my fullest ability. I hope you guys had a good time in watching these videos and had a great understanding, and lit up your brain like those memes that I showed up. And I hope you reach your full potential learning this. And that's all for this chapter. I'll see you again in chapter 8 lectures.